All right, I think we can continue here. So now in this part of the talk we'll discuss how one Haskell module is compiled. So in the continuation of this workshop, we'll talk about just one stage of this compilation pipeline. But in order to get there, we have to see all these stages. So just in the very beginning, we have one Haskell module, and then we want to compile it into something. We'll see what exactly we can compile it to. All right. So if you look at the compiler directory inside your GHC distribution, then you will see Compilation Manager, which is all about looking at several modules, about deciding in which order it is a good idea to compile these modules, something like that. Then there is also the Haskell compiler. So the Haskell compiler is actually single module compiler. And this abbreviation HSC is regular abbreviation inside code base. So it's the Haskell compiler. So we'll talk about it. Then there is also a driver. Some implementation for driver is also there. About pre-processing, about linking, and other stuff here. So we will talk mainly about the Haskell compiler. So in the very beginning, you have just one module, and then you have to get something out of it. So this is, I've taken this picture from GHC commentary. I will show some parts of it shortly, so you don't have to read it right now. But just this picture is for getting some basic idea that it's a long process to compile one Haskell module. So there are many stages there. You can see some loops here, like this one. This is, for example, every optimization is run right there. You can see these three things, like several possible results after your compilation. And in general, there are these 6 main stages which are run during the compilation. So you start with parsing, which is lexical and syntax analysis of your code. I'm not going to talk much about this parsing stage because it's not type theory at all. It's stuff which is well known from 60s when theory of automata was developed, and it's not very interesting in terms of theory of programming languages. So parsing it's another discipline. Yes.
But can you talk about the fact of the syntax tree that is built?
Yes, I will talk about that. Of course, I will talk about the result of this parsing. Of course. Then we have a renamer. Renamer means taking name which was read from the file and convert it to something with more information about where this name was defined. So which module this name comes from, which library it comes from, something like that. Renamer is responsible for that. Then type checker. Type checker is the most important, or for us, type checker is the second most important thing in this compiler. So it tries to type check everything in your code. Then you run, or compiler runs Desugaring, and this is the most important for this workshop section of this compilation. So we will talk about desugaring here most of the time. Then there is optimizer with this desugared code, and then there is a code generator to get something that can be actually run on your system. Okay, so now let's follow. So this pipeline is just the same as these 6 steps. So now let's follow them. Yeah.
You'll probably answer this later, but just to keep it in mind, like why would you want to desugar before or after type checking? Because it seems like you're just making more work for yourself.
That's a very good question, and It is very important for Haskell. Because there are actually several type check-ins in during compilation. So after desugaring, it's almost impossible to go back to the original structure of a program. If you want to provide feedback to your user, it is very difficult to get something useful for the user when you have this desugared code. So the most information you can give is just, well, something is wrong with your program. So that's why you are doing type checking before that. So when you type check Haskell source code, you are very close to the user. You can say, well, this thing is wrong because you don't have this instance of this class type, for example. So this type is wrong because you do not satisfy these constraints or something like that. Yes.
Just to make you honest, can we say that advanced type features which exist in front-end language get desugared to the internal type system language?
We'll see that. So technically, these are different type systems. So in Haskell itself, you have one type system with many of the features available, and something which is desugared, it has another type system. It is at the same time more simple, but it's also significantly more expressive. And we will see that. So these are different type systems. So outer language and this intermediate representation, they are different languages. And we'll talk more about this desugared code because it's exactly where type theory works. So when we are talking about type check, it's type checker for Haskell source code. So it was designed specifically for Haskell, and as such, it is not very interesting for type theory, because type theory is not something about implementing Haskell, implementing type checkers for Haskell. So it's not very interesting for type theory. But when we have desugared code, then it's exactly type theory in its the most common general part. Yes?
Where is the constraint solver in the pipeline?
Constraint solver, you mean with type classes and instances?
Yeah,
It's part of type checking, I think. This for stage 3. Yes.
Is it theoretically possible that you get an error after the desugarer reported as a normal Haskell user?
Well, there is a small chance of that. But generally, in most of the cases, if you see something like GHC panic, it was generated with something after desugaring. So in most of the cases, you have guarantee. So if it type checked, then nothing can be wrong with your code in the later stages. Well, it is possible, but that generally means it is a mistake in a compiler. So if you get something like that, yes.
So the type checker has a more strict type system than the desugarer.
It's not like that. It's again, I'll repeat this phrase. It's a type checker for Haskell language. So type system for Haskell. It's at the same time it's less expressive and more expressive. So there is no simple corresponding.
But the type checker should accept strictly less programs than, or not, well, at least less programs than
it doesn't. No. It doesn't work like that.
But then it could happen that something type checks and is rejected later on.
Well, again, as I said, it is possible, but it normally means it's because, well, why is that? So this code, desugared code, it is generated by the compiler. So that basically means the situation that compiler generates something wrong. So it takes Haskell and then generates something wrong, and then it has a problem with this desugared code. So if everything goes well, it should generate something which is good. So we have a possibility to write something in this desugared code and then feed it to the compiler. This desugared code. And then it is possible to have some problems in there. But I will say several words about that. But not much of yeah.
Is it possible for a desugaring to desugar to code that couldn't be written in Haskell source code?
This type system in desugared code is more expressive. So technically, there are things that can be expressed in desugared code, but cannot be expressed in Haskell itself.
Okay.
So
it's
it is.
It's an AST desugaring rather than a source code desugaring.
Yes, that's right. Okay, so now let's talk about these stages. So this the first two stages, it's parser and renamer. And look here, so this is the beginning of this compilation pipeline, parse and rename. The result of parsing, you can see this name here, hsyn. hsyn is the name of the type for abstract syntax tree. This is a result of parsing. So you have this abstract syntax tree. We'll see several examples what exactly it is built of. But you can see this nice thing. You have this syntax tree here and this syntax tree here after renaming. So it's the same syntax tree, but it is parameterized with different types. So reader name is something that was read from the file. So for example, you have print there. Well, the name is print. But then you have to convert this print into something like system.io.print with full qualification. So it comes from this module, and so renamer adds this information. But it's again the same syntax tree. So these two names, and rename converts them name reader name to name here. So as a result, after renamer, you have fully qualified names. And of course, at this stage, if you have some imports in your file, this is the place where all these imports are resolved. So this is the place where you can get such messages from the compiler that this name is unavailable here. So or ambiguous naming can be. You can get those messages here that several names have this name. So you have map, and please specify exactly which module this map comes from. So this comes from these two stages. Of course, if you have some syntax problems in your files, then parser will tell you. This stage can give you some kind of errors. And in Haskell, it is impossible to get error message about wrong types before some syntax errors or these renaming errors. So if you understand this correctly, these stages, then sometimes you can understand more about your code. For example, I just give you one small example about how this understanding of stages helps a little bit. Maybe you've heard about such extension duplicate record fields. So in Haskell, generally, it is impossible to have same field names in two different records. It is prohibited because from every field name, compiler should generate an accessor function. And it is possible to have two functions with different types, but with the same name. Then there is this extension, duplicate record fields. Unfortunately, when you enable this extension, then you have to specify, in many cases, an exact type of this accessor function. So sometimes it works, but sometimes it doesn't work. You just, you can define these two fields with the same name. That works as a charm. But then when you call this function, you have to say, well, please apply this accessor, but you should specify which type this argument is. So you just say in this code. And if you don't have this specification, explicit specification of type, then it doesn't work. So if you use this extension, duplicate records fields, you may well have such error messages. Yes?
Does this mean that after rename, all explicit types I give a specific accessor or whatever is included in the name data type?
No, that's not like that. But that's actually the reason why we have this problem with duplicate record fields. Because this extension is implemented right now at the stage of the renamer. And at this stage, there is no information about types. So if you specify this information explicitly in your code, then this information will reside in abstract syntax tree. And duplicate record fields is able to use this information in order to find the right accessor function. If you don't specify this type information, and there were no type checking yet at this stage, so if there is no such information in your source code, then this extension is not able to find the right field. And that's the problem. So you have to write these types explicitly. So if you know that this extension is implemented right here, the stage of renaming, and there is no type information, unless you specified it explicitly, then you understand why it is necessary to specify these types. So right now there is work in progress on implementing another extension about it. So, and the right place for such extension would be to implement it somewhere during the type checking. So when you have more information, or even after type checking. And if you implement it there, then you will have more information and it will be easier to do that. But it's really work in progress, and there are other problems with the implementation right now. But that's an example where knowing these stages is useful. Yes?
This also means that all errors about ambiguous names are deferred to the type checking phase and might come up more.
Some of them
are harder to understand then, or not as straightforward anymore.
Right. Right. So, but ambiguous names, sometimes it is possible to report them on this renaming. Sometimes they are on type checking. And in fact, I think. Sorry?
Could that be a problem in some cases when things are suddenly accepted because they're disambiguated because of the type that they don't want? So they really want to be different on.
I think, if I'm not mistaken, there is an extension which allows some ambiguous problems to try to type check some ambiguous names in order to get more information about that. So, if I'm not mistaken, I cannot say that how things are going on exactly. So. I think it is possible to defer some resolving such issues to the later stages. And then you can find the right thing right there. But that's I think it's quite difficult thing. And maybe this problem of implementing this extension amounts a lot to this problem. Different stages and different problems with reporting errors. But that's I cannot say that for sure. Okay. All right. So these are first two stages, and let's see about something about this HS syn data type, this abstract syntax tree for Haskell. So you know that there are many things in Haskell source code. So you can find this type HS module, which is about, well, Haskell modules. We are talking about compiling one module. There is a field for module name here, and you see it's maybe, because you know you don't have to specify this, so it can be module name where, or you can omit this line, and then it will be nothing here. Then you can see the list of exports here, Again, it's maybe because you're not obliged to have it. The list of imports and the list of Haskell declarations. So basically every module is something like that. You have a name, you have export list, you have import list, and then you have list of declarations. And these declarations includes everything that can be right there. There are some other things. I'm not going to talk about them. If you look at the source code, you will see the full definition of this type. So there is information about some comments, compiler pragmas, something like that, even there. But we'll try to look what is inside that. So what is a declaration? So this is the most difficult thing in Haskell source tree. So it's a very huge tree, actually. There are many things in Haskell that you can find in this tree. Here I try to, and this slide, there are the most useful ones. And I will use this slide to show you how it is convenient to understand these prefixes, prefix names. For example, Thai always means type. So Thai, type is very, very long word. So it's always abbreviated to just Thai. So the first declaration is type class declaration here. So type class is just one of examples of some declaration in Haskell source code. Then you can see instant. Yes.
The very first thing. I'm assuming located just means that you know where it is in the source file and you can kind of ignore it.
Yeah, exactly. So like it just gives you information where in the source code you can find it. So of course in this syntax tree it's useful for error reporting. Just to say where this thing is. So type class declaration, then instance declaration, then derivation. This is derivation, standalone derivation. You know that when you declare data types, you can write derive, and that's part of data type declaration actually. So this one is standalone derivation, derive, and then something like that. What do you think about this one? What is it? Val D. Do you have any ideas what can be val here? And that's actually the most important thing here in Haskell source code. Yes?
Is it a pattern there? Is the writing separated?
No.
Can be top level in the module without
Is this just any top level definition? It's not one of these other things?
Exactly. So any top level, so any function that you write in your Haskell code, it's a value. So every function, or if you write just like some constant functions there, so everything is a value here. So val D is value declaration. So any function, everything that you can write there. Then you have type signatures, signatures, type annotation there. Then you have default declarations. It is rarely used thing, I think right now. Foreign declarations for writing something for using external libraries, platform libraries, but that's not all. So this is something that you almost never use. So even if you're experienced Haskell programmer, these are declarations that you maybe you use once. Yes.
This doc one is for header?
Yeah, exactly. So this is head dog declaration. Yeah, you normally you write that. So we have some warning declarations, annotations in Haskell. These are rules for rewriting rules, so-called rules for rewriting. Then vectorization declaration, something about instructions on how to vectorize this code. Role annotations. Here we'll talk in this workshop. We'll talk about these role annotations here. In fact, I don't know what is splice declaration. Never heard.
Template Haskell splice?
Exactly. Yeah, you're right. So you see many declarations here in this Haskell source tree. All right. So now let's go to the next stage, type checking. This is it. And again, we have this syntax tree. And before type checking, this syntax tree is parameterized with name. Now it's fully renamed name, so with full information about where it comes from. And the result of type checking is the same tree with identifiers. And ID here is a name accompanied with a type. So after this type checking, after this step, every name, and in fact every expression, every component of expression has its name explicitly specified. So what is type checking in Haskell? It's not just type checking. It's also type inference, because Haskell has static type system with type inference. So you don't have, in most of the cases, you don't have to specify types explicitly, because they will be inferred during type checking. So you can have some types before type checking, but then everything has its type after type checking. So that's why they changed this from name to ID. So after type checking, everything is type checked, and we have some guarantee that everything is all right with our program. Yes?
So how do you said you have some things that are typed before type checking?
Mm-hmm.
Where do you put the type?
Well, you just declarations like you write double colon and then type.
Syntactically?
Yes, syntactically,
Okay,
absolutely.
types.
Absolutely.
Okay, sorry, I missed that.
Just like that. Well, you may think that this workshop is about this type checking. It's not actually. So this type checking is not very interesting from the perspective of type theory. I've told this already. This type checking is more about Haskell itself. So you have many specific things in Haskell, and you have to type check these class types, instances, or specific values, some expressions. So you want to type check that, but it's not very interesting. Well, of course, if you have something very sophisticated, like generalized abstract data types, for example, in your code, then type inference for them is very interesting. So you can implement it, and then it's wrong, and then you implement it again, and then it's wrong again. Someone finds some bugs in this implementation. For example, with these generalized abstract data types, there were several papers when they tried to fix bugs with the previous implementation. It's pretty regular thing there, but still it's not general type theory. So I will not talk much about this type checking, because we'll have more interesting types later. All right. So you type check everything at this stage, and then you go to the central part of this workshop. So the result of desugaring is so-called core, or GHC Core. It's an intermediate language. So desugaring basically means convert Haskell source code, Haskell source tree, to this intermediate language with the name GHC Core. And then this is an explicitly typed language. We'll see it shortly. You can do many optimizations there. So you see this loop is actually applying many optimizations. You just get this result of desugaring, then you simplify it using specific mechanisms, then you apply some optimization to it, and then you simplify it again. Next optimization, there are hundreds of different optimizations there. Yes?
Is this where things like fmap rewrite rules happen?
Exactly.
Okay.
Exactly. Right here, during this loop, and you can specify which iteration of this loop you can apply it, actually.
Nice.
Yeah. So it's exactly here. So this every modification of your code is done here. And then you do some tidying. Well, it's rather technical. You get some final result of all this stuff here. And now let's talk about this core expression. So it's rather simple. So you remember those many declarations, types of declaration in Haskell source code. This is the whole of the core export type. So everything is converted into this. I just take the latest version, so it's actual. It changes from time to time, but now it looks like this. So every Haskell is converted to this one, and here the place we'll discuss it. I will not say more about these data constructors here, because when we are talking about type theory, we are not usually using Haskell syntax for that. So for doing type theory, we are using Greek, as you know. So the Greek looks like this one, this slide. So this is the same thing that was presented in Haskell syntax, but now it's real type theory. So that's the difference. Basically, that's all the difference between working with Haskell and working with type theory. Is using either Greek or just usual Haskell syntax. Yes?
So, I don't know if this is a question or a comment, but you have like typing, type rules, or like typing rules for whatever, abstraction,
Yep.
that help you guide from this pretty primitive tree to making deductions or whatever. But there's some pretty crazy things you can do with Haskell, like at the type level. I mean, like forgetting even dependent types, but pretty interesting things you can do that you might consider syntactic, but we're just like disregarding because it's part of this initial type checking. But like, there's a lot of things that are really complicated that require 15 or 20 different language extensions that I could do that I have a hard time believing that like there's not some serious reduction or desugaring from that high-level syntax before you can get to this point, like things with certain kinds of equality or partially implied constraints mapped over, like like these things are. Where are they lying in this type?
I like your words very much, because this actually shows one important thing. Well, of course, in modern Haskell, with lots of extensions, you have many very sophisticated things. But in fact, all these things, they just hides the fact that everything is much simpler. So when you write programs in primitive languages like that, like this GHC Core, you can express that thing. So you don't need extensions here. You just work with this very simple language and you can express everything. And in fact, in this language, you can express much more than we have in modern Haskell. So we can implement many other things in this language, apart from what we have currently in Haskell source code. So in fact, in this talk, we'll see many examples how all this sophisticated stuff from Haskell translate into this rather simple language. So everything is translated actually into this simple language. So that's why and this is theory. So in Haskell, we just take all this difficult stuff for programmers and translate it to the very simple thing in the theory. That's it. But you will see. So in fact, everything that I will say in this workshop is answering this question. So just follow me. Yes.
Have you dropped the location information in the GHC Core? Is that the last point where you do?
Let's go back to this source code. So in fact, there is no location information anymore. So it's impossible to go back to the Haskell source code. The only thing, in fact, well, let's make such an exercise. Can you find the difference between actual Haskell core expression here? Just try to memorize all these constructors can you find the difference between this Haskell and this the same thing in Greek? There is only one constructor there. Yes, tick, exactly. Well, when you are working with real world and not theory, you might be interested in some performance characteristics. So this tick thing is used for profiling and something like that. In theory, we don't need that, you know. If this problem is decidable, then we are on the safe side in theory. And it doesn't matter if it's like NP complete or something like that.
It'll finish sometime.
Yes, exactly. We're not, but when we are doing a compiler, when we need profiling. Well, so this tick is the only difference. So no location information, no something like that anymore. Yes.
You say the location information was had to be erased because it couldn't track it through the desugaring because it was
Yes.
explode.
Yeah, because we'll see simple examples of translation, and it's almost impossible to go back to find where this comes from.
Can you visualize desugaring as some kind of unfold where it gets where some small SQ expression explodes to much more core?
I wouldn't say. So it's actually different. So okay, let's.
If we throw away location information, so how does debugging work in this debug support? So they have to thread through some information about the source and
You know, debugging.
Well, you can debug Haskell.
Debugging.
Debug much better recently.
Debugging is a very big problem in Haskell. So you have GHC debugger, which GHCI debugger. You can do that, but that's, by the way, this was a project which was implemented during Google Summer of Code. So it was implemented by the student. And as almost everything implemented by a student, it's not too usable. Unfortunately. as a university lecturer, I know that for sure.
No, but you can load GHC Core generated code into GDB or.
Yeah, but
there is support for that.
yeah, and it's very difficult because it's the problem is that it's very difficult to find correspondence with the Haskell source code.
So the debugger is actually.
Yes, it hides a lot of information. So that's why it's difficult to do GDB debugging, because well you can find something, but it's very difficult to find the exact place in the Haskell source code. So it's very difficult. All right. So here, yeah. Question? Yeah.
This binder here is presumably much simpler than like the bind, because you can do you can do crazy things with binders in Haskell. Like they can be literals, they can be unpacked expressions.
Yeah.
This binder is presumably.
Yeah, they are much simpler, of course. Yeah, sure. I think next slide will be something about these binders. Yes.
Why does it have let at all? Why? Well.
Which one?
Why does it have let? Because you can do let with lam and app. If I guess lam doesn't have bind. That was less clear. But that was less clear.
You see, well, there is a trade-off between pure theory and something which should run on the real hardware. So basically, it is possible to implement everything using just lambdas and application. Lambda calculus is about implementing everything using abstractions and applications.
Yes.
But when you want to make it efficient, you have to use something like this let here, because it will be possible to compile it into something much more efficient than just plain evaluation of lambda calculus. So that's why. So we're not going that down to the basic lambda calculus here. All right. So here you can just there is in these slides there's some information about binders here which we use here. So I'd like to mention one important thing. Please look here. is somebody here know something about ML? ML, not machine learning, but ML programming language. In ML, they have two kinds of let. They have let and let recursive, let rec. So they specify for recursive definition, they use different let recursive. Here you see that we have the same thing here. So binder can be either recursive or not. So in fact, this very close to ML. So it's part of desugaring to find out if we have some recursive definition or just plain let, and we turn them into one of these constructs. All right, so here this is lambda calculus, which is enriched with something. In fact, in the next part of this workshop, we'll talk about how this actually emerged from the basic principles of type theory, how we can come up with all this stuff. So it's not useful to stare at these Greek things here. So we'll come to this from the very beginning. All right. Here, yeah, by the way, it's a continuation of that slide about what can be types here. You can see these for alls here, just arrows for functional types, type constructors, type application, and some other things. We'll move to that later. Then, you know, this was optimization step when you do many optimization. These are just several names for those optimizations. I'm not going to talk about that. So when you have this core expression, there are many ways to make it more efficient, or sometimes less memory needed, something like that. So these are many optimizations which are implemented inside the compiler. And now let's look at this simple example, how this source code is translated. Yeah, it looks like we're close to an end of this part of the section. But yeah, we'll do that. So this is a very simple example of a Haskell program. You can compile it by yourself without even using compiler, because it's very simple. So we have a function, and we have we print result of this function. So what should be result here? Can you compile and execute it in your head?
Hold on, this is math. Crap.
I mean, result should be just this number 5 printed. Yes? Do you agree?
No.
Oh, why? What?
It's num a or like there's 5. It's like 5, but it has no default. Right?
Well, it will be integer number 5. Well, there are many things about defaulting types in Haskell. So if you have these literals, they will be integers here by default. So and even if originally there's num a, it will be integers anyway. All right. So you can run it as follows, and know this flag, dedump simple. It's dumping simplifier stage. So you remember that simplifier. So it will just give you what it has at this stage, at the stage of optimization. All right. So if you do that, you will see something like that. So basically, this is GHC Core. So you see that there is no function f anymore. So it was optimized, so it was inlined here automatically by the compiler. But still you have function main here, you have print here. You have many things like that. And our goal is to find out where it comes from. What does it mean, this symbol with integer? You can see this is plus addition. It looks like a bit of Lisp here with prefix notation here and parents. So these are instances. You see that it's really integer. So this is instance of show class type class for integers, and this is num instance for integer. So we have them here as an arguments to this plus. So that's it. So this is core, an example. And this quote is, it is very good for finishing this part of the workshop. So in that article, which I mentioned in the very beginning, its authors wrote that this core was incredibly stable. And they say in this quote that for 20 years, they've just added one simple addition to this core. So Haskell evolved enormously, and that's absolutely true. For that time, we've implemented lots of things in Haskell, but core itself was very stable until recent years. In fact, this 2012, it was the last year of stable GHC Core. And everything that comes after that, we'll see it today in the rest of this workshop. So it's constant. Every year, this GHC Core changes a little bit. And this change was quite interesting, actually. It's not just something like making it more sophisticated. Some of the changes were opposite. We made them simpler. And current GHC Core is the simplest core we ever had in Haskell, in GHC Compiler. So now it's simpler than it was in 2012. Well, in some points it's simpler, yes.
Does it mean that also more work might have shifted to the simplifier?
Yeah, of course, but you know, it is very good to have simple core.
But it might come back to this question, you know, maybe we do more work now on the high-level language, and it is a simplifier and the core language. You know, if you have assembly code, that's very simple too, but it's very verbose, and you might not have so much structure to do optimizations anymore.
No. You know, the problem with this idea is the follows. If we can simplify core, we can use simple core, but it can use different type system. And you can have a richer type system, which is expressed with smaller amount of constructions. But it is richer.
Compiling or desugaring might throw away a lot of structural information about your program that kind of you lose knowledge about the program possibly. I don't know.
It's not the case. I think I will prove that it's not the case during the several other sections of this workshop. So, but still, this Bravo Gerard. Do you know who is this Gerard?
Someone who came up with the core.
Yeah, it's logician who invented or discovered system F, so-called polymorphic lambda calculus. Gerard, and there is also Reynolds, who does the same thing in the realm of theory of programming languages. So if you know this, if you heard about Curry-Howard correspondence, that's Gerard was logician part of that, and Reynolds was programming part of that, type theory part of that. So they two created this system F. But we'll talk about this system F later in this session. So now I think it's 1 hour break for lunch. So we'll continue here in 1 hour. Yeah. Okay. Thank you.